Okay, everybody, we're going to be talking about the more common chi-squares. Last class we talked about the chi-square goodness of fit test, but just like we started off doing null hypothesis, where is our sample a stated value. Most of the time we do what we did in chapter 10, which is, hey, we have two different samples, are they the same, or two different populations? And so that's what we're going to get into with the chi-square. Is we're going to be talking about this. And so, we'll be looking at data in a two-way table. And when we say two-way table, I mean a table that looks like this, where there is two different variables, which each one of them has multiple categories that we're looking at. And we did two-way tables way early in the year, but they're going to come up again. And so in this section, we'll start out by developing it as a test to determine whether the distribution of character variables is the same for each of several populations. In next class, we'll determine whether there's an association between the rows and the columns. And this is what we'll be getting into in the next video. So what are we going to be doing today? Well, we're going to be doing problems like this. Market researchers suspect that the background music may affect the mood and buying behavior of customers. One study in a supermarket compared 3 randomly assigned treatments. They played no music, they played French accordion music, and they played Italian string music. Under each conditions, the researchers recorded the number of bottles of French, Italian, and other wines purchased. Here is a table that summarizes the data. So we could find the probability, we can break this data down, and that's what we're going to do here in a second. So how do we test if it didn't affect anybody? And what we will do is we will do a chi-square test for homogeneity. How is that different than the goodness of fit we just did? Well, we don't have a set pattern. What we're saying is, are the patterns in all the different treatments the same? So the problem with how to do many comparisons at once with the overall measure of confidence in all our conclusions is common in statistics. We've talked about multiple comparisons. We don't want to do multiple significance tests because there's a 5% error that means that there's a 95% chance that we're right, but then the second time we do it, if we do 2 of them, there's only an 81% chance we're right on both. And the problem, that's not correct. 95 squared is, make me get my calculator. Look what you drive me to. If we do 2 tests, there's only a 90% chance we got them both right. If we were to do, say, 6 tests, there's a almost 27% chance we'll get one wrong, even at the 0.05 significance level. And I can explain that further in class. Ask me. So generally what we're going to do is we're going to do an overall test to see if there's good evidence of any differences among the parameters we want to compare. And then we do a follow-up to decide which parameters difference and how big they are. And that test is what's known as an ANOVA test, which stands for Analysis of Variance. The good news is that the ANOVA test is not on the AP exam. So we won't be discussing it. So we'll just be saying there is a problem. We will not be saying what the problem is. So to perform a test in this thing, to perform the chi-square test for homogeneity, what we will be looking at is our null hypothesis: there is no difference in the distribution, and the alternative is that there is a difference. So going back to our two-way table, our null hypothesis is that there is no difference in the distribution of wine bought, right, regardless of how the music is played. So the same percentage of French wine was bought regardless of what type of music was played. The same percentage of Italian music or the same percentage of Italian wine was bought no matter what music was played, so forth and so on. And so that's what we're looking at. That's what we're looking at. So for each treatment, right, this is one buying thing. So when they played no music, 84 bottles were bought. And 30 out of 84 were French. When they played French music, 39 out of 75. When they played Italian music, it was 30 out of 84. And so the question is are all these percentages close enough that the music had no effect on the purchasing, or are there differences that are so large that they cannot be there has to have been some kind of change made? So how do we do that? Well, what we are going to do is we are going to compare the observed to the expected counts. And so the hard part is, how do you get the expected counts? Well, what we want to do is say, what was our total? So total, 99 bottles of French wine were bought out of 243. So if they were all the same, remember, all our hypothesis testing is going on the assumption that the null hypothesis is true. The null hypothesis is that there is no effect. So regardless of what music was played, then 99 out of 200, this proportion, right, whatever that is, oh, sorry, let me get that number. 99 divided by 243 is around 40%, so around 0.47. So regardless of what type of music is played, around 40% of all bottles sold should be French. So what we do is we take that number, that 99 out of 243, and we multiply it by the bottles of wine sold, and we will get our expected counts. And so, we would create a new table with expected counts like this, and instead of writing these numbers in our expected count table, we would write these numbers. And we would do that for each one. So to get the Italians, we do the same thing, but this time we would look at, okay, overall the percentage of Italian wine bought was 31 out of 243. So then we multiply each one of those by the total number of bottles bought under each treatment, and we get expected counts. And then for the, once again, same thing, other types of wine, which is the 11 out of 243, and then we multiply it by this. And what you will see is that there is a pattern. And the pattern is the expected count equals the row total times the column total divided by the table total. Right. So to get the expected count that would go here in our new matrix, or here, let's do one that's on our board. So to get, we're going to create a new way table just like we had before with the expected counts. We want to get this one. So we'd go this divided by this, this times this divided by this, or 113 divided by 84 times, 113 times 84, row total times column total divided by table total, which, if you will see, is exactly what's written right there. And so we would have to create a whole new table, two-way table, with the expected counts. Once we have the expected counts, in order to create the test, the conditions for the for the homogeneity test are the same as for the goodness of fit, which is random, independent, and this is treatments are assigned independence. We sampled less than 10% of the wine buyers, and what happens in one doesn't affect the other. And then instead of normality, we have large sample size, and that means that all expected counts must be greater than 5, greater than or equal to 5. So let's look at the one we just did. So in here, if we go, actually I think I have it here, maybe. So here are your expected counts when we did it. So here is our observed, here is our expected counts. So in order for it to be the large sample size, all expected counts must be larger than 5, and they all are. Great. They were all randomly selected. The random conditions met because treatments were assigned at random. Now, we're comparing 3 independent groups in a random experiment, but are individual observations independent? And this is where we get into that independence getting a little sticky. Is if someone buys 1 bottle of wine, does that affect them buying another one? Like if someone buys Italian, are they more likely to buy 2 bottles of Italian? And so it's a little sticky. We'll proceed with caution, right? Whenever we get into sticky, we're going to go ahead, but we're going to proceed with caution. The chi-square has not changed. It's just observed minus expected divided by expected. And so to calculate your chi-square, here are your observed and expected counts. And so it's just 30 minus 34 divided by 34, and there's the square. 30 minus 34 squared divided by 34, and you add them all up, and when we do it, we would get a chi-square of 18.28. Now, the only tricky part is how we determine the degrees of freedom. Right, and this is just review how we set the null hypothesis, random, large sample size, independent conditions, chi-square. Degrees of freedom is number of rows minus 1 times number of columns minus 1. So if we go back, there are 1, 2, 3 rows and 1, 2, 3 columns. So that is 3 minus 1 times 3 minus 1, or 4. So in our example, we will have 4 degrees of freedom. And so if you go to your chi-square distribution in the back of the book, you will see that 18.28 falls between, in here somewhere. So it's between, it's greater than 0.0025, but it's less than backwards. It's less than this, but greater than that. But either way, we're definitely below 0.05. Right? The first 2 decimal places are 0 or below 0.05. So the small p-value gives us convincing evidence to reject the null hypothesis and conclude that there is a difference in distribution of wine purchases at the store when no music, French accordion music, or Italian spring music is played. Furthermore, the random assignment allows us to say that the difference is caused by the music that's played, because this was an experiment. All right, and then I'll show you how to use the calculator to do all this stuff in class. The one thing that I want to talk about, and this is bonus material now, is in real life you'd say, okay, well, great, there was a difference. Where is the difference? And this is where that ANOVA we came about, the analysis of variance test would come in. But if we look at it, here's computer output for the chi-square test. And it's got the observed, the expected, and then the piece of the chi-squares. Right, and how different are we when we do this? And what you'll notice is almost the entire difference came when French music was playing, and the first treatment was French wine. Second treatment was Italian wine. I think the third treatment was no music. Let's go back and double check that. Yeah. Or is this, did I get that backwards? And so what you're seeing then, let me just double check, is the treatments were the type of music played. And so what we're seeing is most of it is when the French accordion music was playing, people were much more likely to buy French wine. Almost and they were a lot more likely. So actually, it's the Italian music. Sorry, I'm wrong. The Italian music here, this is what's making up the bulk. These two things right here are 13 is the majority of our chi-square test. So it's really the Italian string music, that's really making the difference here. And the analysis of variance would show that. And so if they ask you, on the AP exam, they won't ask you, they might ask you which component of the chi-square do you think is the biggest difference. And so you'd be looking for which piece gave you the largest chi-square value. So that's it. We'll see you in class next time.